All right, hey everybody. Well, I think we're getting started now. People are still trickling in, getting some food, but okay. Good morning, everyone. It's my great pleasure to introduce Dr. Peter Driscoll, who's visiting us from the Carnegie Institution for Science in Washington, D.C. And Peter was actually my postdoc advisor when I was a Carnegie Fellow a few years ago, just before the pandemic. And like me, Peter has kind of moved back and forth across the country a number of times. I think you're originally from Philadelphia, and then he went to a school for physics and astronomy nearby at was it Dickinson College, and then he decided to move all the way to the West Coast and went to San Francisco State University for a master's in physics and astronomy, and then all the way back to the East Coast for a PhD in Earth and Planetary Science at Johns Hopkins University. And then you stayed there for a minute and went to a postdoc at Yale, right? And then back to the West Coast and another postdoc at the University of Washington in Seattle before finally coming back to the East Coast and settling in Washington, D.C. And for those of you who know Carnegie, it's the Carnegie Earth and Planets Laboratory now. It used to be, it was a merger of the Geophysical Laboratory and the Department of Terrestrial Magnetism. And I mention that because I think the sound of the name Department of Terrestrial Magnetism is super cool. And it has a cool history too. Like was that 1908 or something it started? Anyways,
1902, yeah.
1902. And they started with these expeditions like on like sea voyages where they were zigzagging across all the oceans and mapping out the Earth's magnetic field for the first time. And so it was a really cool, I think, start of that thing. And then they kind of got into other research and they went and drifted into some other things. And then at one point, there was no one there really working on magnetism until Peter came. And then so Peter, for a little while, when he first got there, he was kind of the only person that made the place's name make sense because he works on terrestrial magnetism. He does a lot of core dynamic simulations. You'll probably see some cool 3D simulations here in a minute, studying the magnetic field of the Earth and other planets. And yeah, and I guess we're going to hear about that now in a second. But I'll also say Peter is very open to interactive sort of discussion here. So feel free to interrupt him as you go along. And with that, let's welcome Peter.
Okay, thanks. Okay, thanks. Thanks, Doug, for the introduction and the invitation, and thanks to everybody for coming. I'm very excited to be here. I've heard a lot about UTIG, and I know enough number of people here, so it's very exciting to be here. And for a couple of days, I hope to come back at some point. Austin's pretty cool. Yeah, I like traveling. Yeah, I was the senior terrestrial magnetist there for a couple of years. I was the youngest faculty, but the only person studying terrestrial magnetism. And then they took that self-proclaimed title away from me when they changed department names. So, but we are the Earth and Planets Laboratory now, same science, just a different name. And my talk today is not really a detailed research talk, so there's no like sharp punchline at the end. What I'm gonna do today is give you an overview of how I see our understanding of planetary magnetic fields and how they evolve. Oh, we have to get Zoom going here or something. Yeah, I think this is being recorded, right? Okay, thank you. So let's get into it. So here's what I have in mind. I may not get through all this stuff. We'll see how it goes. And yes, please ask questions as we go. That's fine, because it's kind of like a lot of fundamental understanding I'm trying to convey here. So questions are good. So I'm just going to sort of go through this outline of describing why the magnetic field we think is important for planets. I'll go through a survey very quickly, of the solar system magnetic fields, and mostly just the rocky ones. And then I'm going to go into some of my work over the last couple years on dynamo theory. So if you're familiar with the dynamo theory literature, some of this stuff might seem old to you, but if you're not, which I think most people are not, then some of this stuff is going to be new. And then if I get to it, step 4 will be like a research vignette that I've been working on recently, trying to pin down the age of Earth's inner core. And one principle that I find that I follow more as I get older is something that has been attributed to Einstein, even though I'm not quite sure he ever said it, was that everything should be made as simple as possible, but not simpler. So I really strive to take stuff like dynamo theory and MHD to its simplest. And so hopefully that comes through today. I'm not going to blast you with a lot of complicated fluid mechanics, okay? So first, why are magnetic fields important? This is a not to scale sketch that someone at Carnegie drew. Yeah, I mean, I guess it could be scale for some other exoplanet, but not for Earth. But it illustrates the principle that the Earth's magnetic field is kind of like this electromagnetic bubble in space, where a lot of the solar high energy particles are funneled around this magnetopause boundary here. Some of them get down into the dipolar field lines that are mostly organized near the rotation axes of the Earth. And so you see these kind of aurora in the atmosphere where these particles hit neutrals and generate photons and stuff. And that's isolated towards the poles because we have a dipolar magnetic field that is close to the rotation axis, okay? So this is the magnetic shield I was referring to. People think that it's important to have this kind of shield to protect the surface from high energy charged particles, or at least funnel them towards the poles so that most of the surface is shielded, at least, maybe. Two other really interesting things about magnetic fields from a geophysical point of view is that they are remotely detectable. Folks at Carnegie DTM detected Jupiter's magnetic field in 1955 by accident. That was the first planetary magnetic field detection. And that technique is being used today in NASA to build out a big project to look for exoplanet magnetic fields using a very similar technique, which I might get to at some point near the end. And then most importantly, I think, is that the magnetic field gives you a unique window into the deep interior because these magnetic field lines tell you what's going on about the convective flows in the core itself, which is something you obviously cannot get to. We have no access to. We just have seismology, more or less. We have no samples. So it's a really valuable tool to have this remote capability. And then just some more motivation for why we think magnetic fields are important. There's a couple papers here where parts of these papers were about the importance of magnetic fields. And here's a sketch of maybe an Earth-like planet where the magnetic field does a good job of protecting the surface and maybe helping retain hydrogen and water for long periods of time, which may be important for things like subduction and plate tectonics. And plate tectonics and subduction are good at drawing heat out of the mantle, which is good at keeping the magnetic field alive longer. So there's like a stabilizing feedback loop here potentially that the Earth has, or maybe has had for billions of years. And then something on Venus, this is drawn as like a super Earth, but something on maybe with a stagnant lid, no magnetic field, sort of no volatiles, no hydrogen, no water on the surface. And so you have this negative feedback of shutting down the magnetic field. So there's more of this concept of this whole planet coupling in these series of papers, and I recommend you go look at those. And I'm happy to talk about those more if you're interested. So let's situate ourselves in the solar system. Planetary magnetic fields are ubiquitous. Here's a plot of magnetic field strengths versus object mass. The sun is on there. Gas giants are on there, rocky planets, and then a couple satellites. I will point out, obviously, that Mars has a dead field, or we think is a dead magnetic field. Ganymede has an active field. Io has an induction field. Mercury's is active. Europa's is induction. So that's what those little symbols are meant to mean. And there's kind of a zoo of magnetic field morphologies, tilt angles, and so forth. So it's not just one size fits all. It's not just a simple dipole. And then the reason why there's so much diversity to some extent is because when you think about the actual flows that are going on in the field that's being generated in the core, it's very complex. It's a very turbulent, time-dependent, chaotic process. This is from a numerical spaghetti diagram from Gary Glotzmeyer from way back in the day. And this you see this figure all over the place on cover of textbooks and stuff. It's really great. And it just gives you a sense of like going from a very complicated process to a very simple process on the surface. So it's kind of, a lot of the dynamics are really hidden in the core. So just to show you a little bit more detail about these planets' magnetic fields and what they look like, here I'm showing figures from, mostly taken from Krista's review paper with the late great Jerry Schubert, and then some updated ones we put on here. Me and my colleague Marie Heimpohl have this review paper that it's actually still not published. It's been accepted now for 2 years, but it's not out there yet. I should put it on an archive. Mercury's field is very dipolar. Earth's field is mostly dipolar with a little bit of non-dipolar. Jupiter's field is also very dipolar, and this is just newish data where we can actually see some non-dipolar features, which is interesting. Saturn at its surface is extraordinarily axially dipolar, almost to the extent that it's impossible. And so there's some interesting questions there. Uranus and Neptune, to the extent that we understand them, are very bizarre. But of course, these are very limited data sets. It's very hard to get this data. You have to go fly by Uranus and Neptune. It would be great to get radio observations of Uranus and Neptune. I'm not sure that that's been done. Ganymede, I'm showing here. I'm not showing here because it's just a boring dipole. Okay, it didn't make the cut. For the other planets, we have Mars crustal field here, very scattered all over the place. The Moon's crustal field, very distributed, not very simple. And these are ancient fields that have been locked in to magnetized sources in the crust. And so these fields are no longer changing. The dynamo's dead, but at some point, we think they had a source of magnetism that got locked into the crust. And Venus is the outlier because it's next to impossible to put a magnetometer on its surface because all your electronics melt. But it's also maybe the magnetization doesn't remain in the rocks long enough to hold a crustal field. And so this is one of the reasons why we're going back to Venus, is to sort of take a closer look, if possible, whether there's crustal magnetism there. So as I just mentioned, there's lots of magnetic fields in the solar system, but there's only 3 ingredients you need to get these planets to have magnetic fields. And maybe that's why they're so common. First is planetary rotation. This one's another ubiquitous feature of everything in the universe rotates, whether it likes to or not. 2, you need a large electrically conducting fluid somewhere in the interior. And this is also extremely common. Basically, every planet we know of has a large electrically conducting fluid. It need not be iron in the gas giants, which I'll show in a second. And then third, which I think is the real choke point, is the energy supply. Is how are you going to get that liquid iron or that liquid hydrogen to continuously convect or move over time to induce continuous magnetic field, even though it wants to decay away. So that's step 3. We're going to focus a couple more slides on what is the energy supply, where does it come from, and how it can be maintained for billions of years. Okay. So just a nice graphic here from NASA illustrating that we can have large electrically conducting cores made of liquid iron in the rocky planets. And then in the gas giants, it's metallic hydrogen. So at a high enough pressure and temperature, hydrogen becomes like a metal. Its electrons are free to kind of roam around. And then Uranus and Neptune are kind of ice phases. We don't quite understand, but something to do with conductivity of these high pressure phases as well. Okay, so Mercury, here's some data. Actually, this is not data, this is a model of trying to look at what is the inner core size on Mercury given its gravitational and moment of inertia and gravitational field. And so it looks like a couple studies seem to show that there is probably a pretty large inner core, about half the radius of the full core in Mercury. That may be playing a big role in driving the dynamo because presumably that inner core is growing slowly, which can introduce some additional energy to help drive the dynamo. And here's a figure. There's an interesting feature of Mercury's dynamo that the magnetic field has shifted. It's dipolar, but it's shifted north 10 degrees or so, 15 degrees. And so there's this numerical model by Hao that shows one way to get this kind of asymmetric field. But for me, the biggest question about Mercury is why it still has a dynamo after 4.5 billion years. It's a small planet. It has a thin mantle, so presumably it's cooling pretty quickly. And I'm going to come back to that when I get back to my synthesis in a couple slides. Okay, so now let's move on to the moon. Much smaller object, obviously tiny core. The crustal features are very scattered and in all kinds of directions. If you try to fit a dipole field to one or more of these crustal sources, you find poles all over the moon's surface, which indicates either that the moon was undergoing some very strange rotational dynamics in between these events with a dipolar field, or perhaps it wasn't a dipolar field at all, which I think is more likely, and the field was perhaps very unstable. The lunar paleointensity record has been growing steadily over the years. Here's a review by Evans and Tiku showing that it looks like there's a strong field epoch, kind of a die-off, and maybe some kind of resurgence later. If you believe some of those data points are kind of under scrutiny right now. But the magnetic field is dead today. There is no dynamo today, just the crustal field. Okay, same on Mars. We think the Martian crustal field died pretty early on, maybe about 500 million years after the planet formed. We have these strong crustal features. They're predominantly in the southern highlands, which is interesting. They're very kind of scattered and distributed. I think it's very difficult to put together a dipole location or its evolution over time, which is the game we play on the Earth, because these field sources are all over the place again. So kind of a very complicated picture when you look at the crustal field on Mars. Okay, and now I saved the best for last is the Earth's field. Obviously, we know way more information about the Earth's field. So I want to take a couple slides to walk you through what we know about Earth's field. It's something like 4.2 billion years old, or the oldest magnetized samples that have been preserved in zircons since that age that seem to hold a remnant magnetism. These are still very highly debated data points, but something like 3.8 to 4.2, 4.3 billion years ago, we think we had a magnetic field. The data record goes all the way up to present day. It looks like the magnetic field has been around forever, since the Earth formed, as far as we can tell. The movie on the top is showing you a much more recent time scale of the last 10,000 years, and it's very slow, so I'm just going to pull through it, just to give you a sense of what the time scale is for the fluctuation of the field. It's sort of pulsating these, it's very dipolar, but it's pulsating these kind of non-dipolar features. You can see the magnetic equator here, the solid line kind of slowly modulating. So this is what a real dynamo looks like on a 10,000-year time scale. This is kind of like the variability time scale for a planetary magnetic field. So I suspect other planetary magnetic fields today have similar kind of changes if we had the kind of data sets, but we don't, obviously. Okay, the magnetic field, the dipole, of course, was not always in the same orientation that it is today. It's reversed thousands of times. And down here on the bottom right here, I'm showing a plot of the magnetic reversal frequency. So it's currently reverses about 5 times per million years, so about once every 200,000 years. But it's random. It's not regular like the solar reversals. And if you go back over the Phanerozoics, the last 550 million years, you see this interesting modulation in the reversal frequency from about 5 today down to 0 during the most recent superchron, where there were quote unquote no reversals for about 40 million years, interestingly enough, and then a ramp up, and then a very active Jurassic period that people are studying, a ramp down to the Kaiman, some lack of data, and then another identified superchron in the Moyero, and then maybe some craziness around 550, which is going to get to my inner core story if I get there. But I just wanted to point out that this kind of record tells us a lot about what the deep Earth is doing over time, because this 200 million year timescale for this modulation is not a dynamo timescale. The dynamo timescales are like thousands of years, hundreds to thousands of years, very quick. Okay, the reversal takes about 5,000 years to occur. This timescale is a mantle convection timescale. So it's much more likely that the mantle is reorganizing or undergoing a plume cycle, or an oceanic, the classic Wilson cycle or something, to cause this kind of modulation. So folks have been looking for proxies for like maybe the seafloor spreading rates and trying to line them up here with the reversal rates. So there are a couple papers showing that there's a correlation there. But the full mantle convection models coupled to the core convection models, which a couple people have tried over the years, don't reproduce these data very well. So there are some issues there, and that's a whole nother talk that I'm not really going to go into, but if we simplify the game a little bit, we just focus on the paleo intensity. So this is in these funny units, this virtual axial dipole moment in zeta ampere meters squared. The important thing to notice here is to keep in mind is that the current average is this brown line here, and all these data points going back over the last 3.5 billion years are from individual sites, rocks, samples, and then the time average, I drew a time average in here. It's this wiggling red line, I guess. And then the error envelope indicates the sort of the standard deviation, the standard error. So, okay, takeaway. The field intensity on average does not appear to have a big trend. Like if the Earth is cooling or heating up, I don't know, like you would see a trend, right? But we don't see a trend, which is interesting. First observation. Second observation is the field, the sampling density is very uneven. See like this big region here where we think the inner core nucleated, hint, hint, there's no data. So why is that? That's a bit weird. So folks are going now to fill in this interesting time frame. And why is there no clear secular evolution? This is a fascinating question to me. And this is something we can test by looking at how the dynamics might have evolved over time. So now I want to get into a bit of what generates a magnetic field. I've talked a little bit about driving convection. Again, it's one of our main requirements for maintaining a dynamo. And you may remember from physics 101 that you put a charge in motion, it's going to produce a magnetic field. But that's not exactly what's going on in the core. It's a fluid. It's not ionic. It's a metal. So you need to put it in fluid motion by convection, and it needs to have this kind of circular induction, a large amount of helicity. So it needs to be sort of organized into these vertical columns. This is an old diagram from like the 80s. And this is an easy way to induce a poloidal magnetic field, like a dipole field, right? It's a very simple way of thinking about it. But when you actually do the fluid dynamics, you get, here's a cut here from one of my models, just to give you a sense of how complex the flows are. That's the magnetic field. That's not the flow. So that's the theta, or the vertical magnetic field in the equatorial plane in a dynamo model. That's actually not all that Earth-like in its parameters, but has an Earth-like dipole field. Okay, so that's just to keep in mind. Now, thought experiment, because that last slide might not have, you might not have really comprehended what is actually going on in the dynamo to create this magnetic field. So let's do a laboratory experiment, which I think is a little bit easier to comprehend. There are some things that are impossible today to do here. This is why it's a thought exercise, because you need a tank of electrically conducting fluid at room temperature, which is, you can do it, it's gallium or it's sodium, but these are very expensive and dangerous fluids. So typically we don't have the budgets or the motivation to do these things. But if you did, you would get a big tank, you'd put it on a rotating table. You rotate that table at big omega, you put an ambient laboratory magnetic field through it, and you put a propeller in it. That's the way we're going to drive the convective currents. So instead of having thermal cooling or anything, we're just going to manually just stir this thing. So the first thing you do is, once you get everything into steady state rotation, is you spin your propeller, you counterspin your propeller or something, just create some turbulent flows in there. And those turbulent flows will start to induce a secondary field, B1, that will have its own dynamics and orientation. And then the question is, are you stirring it hard enough or rotating it fast enough, or your electrical conductivity is high enough to maintain a dynamo or not? So you remove the external field, B naught. So pretend that there's no B naught here in this diagram. And then you wait, you keep doing your stirring and your spinning. And if you wait and wait and wait, and then the field just decays away and dies, then you've failed. Your experiment is a failure. The magnetic field is subcritical in this case. But if you've succeeded, then you're supercritical for dynamo action. And this magical dynamo parameter, which is the magnetic Reynolds number, which is the fluid velocity times the shell thickness over the magnetic diffusivity, has a magical threshold number of about 40. So just like the onset of convection has a critical Rayleigh number of 660 or so, or 1,000, there's a critical magnetic Reynolds number over which the threshold for dynamo action is reached. And that's a nice handy way of thinking about that. And that doesn't depend on whether it's a planet or a laboratory or a box or whatever. Okay. So in an actual planet, we don't have propellers, but we do have a lot of heat from formation and some radiogenic heat and some other small heat sources that are constantly trying to get out. And sometimes they want to get out so bad that they cause convection, which happens in the Earth mantle and in the core. And there's at least these three modes of driving core convection. There's the purely thermal version where you're drawing enough more heat out of the core than it can conduct without fluid motion, right? So it has some conductive limit, and if you exceed that conductive limit in the CMB heat flow, you'll start to drive flows. So that's thermal convection, sort of top driven if you want, dropping cold plumes down and so forth. And then if your core gets cold enough, you'll start to grow an inner core at the center, and that will release light elements and create buoyancy at the bottom. And of course, you can have both. So the Earth is most definitely in this regime, possibly this regime, somewhere in between, possibly. And just to zoom in a little bit closer onto what I mean by the heat flow, is you have the heat flow on the top of the core. So here's the core mantle boundary. The heat flow coming out of the core is controlled by the heat flux in the base of the mantle. So it really is determined by the viscosity of the mantle, the conductivity of the mantle, whatever the mantle wants to, however much heat the mantle wants to pull out of the core is what it's going to do. And then the core just follows along and says, okay, I can conduct this much heat based on my material properties, so the conductivity of iron and so forth. And if this exceeds this, if the QCMB exceeds QK, then you've got thermal convection, and if it doesn't, you don't. So that is one way to drive dynamo action. Just draw a lot of heat out of the core. Okay, that's what I just said. QCMB greater than QK. Okay. Okay, what about compositional convection? So here I'm plotting temperature versus radius again. And here in the red is the iron liquidus or solidus, if you want. And then the black is just a geotherm, a temperature curve, say early on in Earth's history when it was hot and it was fully liquid. You're above the solidus everywhere. And as the core cools, it starts to intersect this curve. And right where this intersection occurs is the boundary between the solid iron and the liquid iron. And this boundary just goes from the bottom out, just from this curvature of these two curves, these two lines for the Earth. It could be different. They could orient differently depending on your planet. But this is a bottom-up style of inner core growth. Right. So it produces so it's just sort of a canonical inner core growth history. It has this kind of quick growth at the beginning and then a flattening off as it goes. Okay, so here's my synthesis. This plot's a little bit busy and a little bit silly, but it's for a reason. And I'm calling it the Goldilocks cooling rate partially because I have two daughters, and this is just the words you come up with. And my daughter drew this on my AGU poster, so I had to show that up here. But the reason why I call it that is because I really think it's the core cooling rate that controls your magnetic history. So if I could break it down to one thing, it would be the core cooling rate. So I'm going to walk you through these three pots of cooling rates, these three options, okay? So the first is the low CMB heat flow, or slow cooling. And in this case, you know, all the planets are presumably going to start out pretty hot from formation, and then they're going to cool off to some extent. And you can drive a thermal dynamo perhaps in the first 500 million years or a billion years, like Mars and potentially Venus, although we don't have that data yet. But then at some point, you're cooling so slowly that you run out of that heat transfer mechanism. So the dynamo will just stop. And, you know, you're not going to reach core crystallization, and your magnetic field history might look like this. Okay, and my question marks here are doing a lot of work because, as you may know, there's a recent paper claiming Mars has an inner core. So that complicates things here a little bit, right? So keep that in mind. Not that I think that that paper is a slam dunk case. That's a whole nother conversation, but it's just keeping that in mind. Okay, what about the medium core cooling rate? You pass through the same thermal phase initially after formation, but then at some point, your inner core will start to nucleate and you've got this compositional source of buoyancy, which can last you for billions of years longer, potentially, until you fully solidify the core. So your magnetic field history, if it was built very simple, might look like this with the sort of thermal decay field and then a boost associated with the inner core growth. And that keeps your dynamo alive for a long time. So really good. Really, you really want to be in this medium core cooling rate. And Earth, we think Earth has gone through this history. Mercury, as I mentioned, seems to have a large inner core, so probably went through a similar history. Ganymede, possibly. We don't know much about Ganymede, but I throw it in this pot for now. And then at the other extreme is the really quickly cooling planets, maybe because they're small, or maybe because they have high conductivities or something. Is you pass through these phases very quickly, or relatively quickly, and then at some point the core becomes fully solidified, like what I think has potentially happened on the moon and Psyche, although of course we don't know until we get to Psyche. So the magnetic field history would look similar to the previous, where you have a bump, inner core growth, and then just die at some point due to full core solidification. So the reason why I put the moon here is because it does, there's been some argument that there's a secondary peak in the paleo intensity and seems to last a little bit longer than we think. So, but we don't know, obviously. I mean, we do think that the moon has some liquid at the base of the mantle, and there's some debate whether it's liquid in the base of the mantle or liquid in the core. And so until we put some more seismometer on the moon, I'm not sure we know the answer to that one. So the takeaway here being that you don't want to be too slow, you don't want to be too fast, you kind of want to be right in the middle to have a magnetic field for a long time. Okay. How do the material properties affect the magnetic field? This is a big question where I work because a lot of people study high pressure material properties, all of these material properties. And so I'm thinking a lot over the years about what role these individual material properties play in the dynamo. So, well, I already introduced this magical magnetic Reynolds number. And you can see there's a U, a D, and a eta here. So you've already got some material properties. So for getting the velocity, it's really the mantle thermal conductivity, the mantle viscosity, the mantle radioactivity. On the core side, it's the core thermal conductivity, adiabatic gradient, the temperature gradient, which is controlled by these thermodynamic parameters, the thermal expansivity and specific heat. The compositional inner core growth is controlled really by the core liquidus. What is the composition of the core and what is the solidification temperature of the core? That's going to be different for every planet, every pressure, right? And what are the light elements that are being rejected at this boundary? Is it sulfur? Is it oxygen? Are there no light elements? In which case there's no compositional convection. And then the last one is the core electrical conductivity, which is inversely proportional to the diffusivity, which is what I want to focus on next. So the electrical conductivity you think of as being really important, because if you don't have a metal, you're not going to create a magnetic field, right? So the material property that's gotten the most attention in the last decade and a half is the thermal conductivity of the core, so the little k. And in a metal, we know that this Wiedemann-Franz law, its empirical law, typically holds. And it says that the thermal conductivity and the electrical conductivity typically evolve together, and with this L being a constant and T being the temperature. And so, at least in a metal, you expect both the heat and the electrical currents to be transported by the same thing, being the electrons. And that's why this law holds. Now, as soon as you have an alloy that's non-ideal, then this can be, you can differ from this a bit, but not massively. So it's a good guide. The thermal conductivity, unfortunately, in the core, we didn't know it back when I started grad school. We just had a couple guesses. And then people started making measurements in the lab, and they were finding, we got a big problem here. It looks like the core conductivity is so high that we have no chance of driving fluid motion in the core. unless we have an enormous core mantle boundary heat flow. So that was a bit of a crisis. And now people have really started to make a lot of measurements. And these are all over the map. You see some are like really low and some are still fairly high. They were kind of converging. I put Pozo here. She has a nice paper trying to bring everyone together and agree on, okay, this experiment's there, this experiment's here, but let's say it's about 80 because everyone's got some approximations and some assumptions in their papers. So I'm sort of operating under this paper's conclusions that we're sort of in this 75, 80 watt per meter per Kelvin range, but still looking for more data on that. So back in 2012 and 2013, when these data first came out, Peter Olson pointed out that there's this high thermal conductivity is a real problem. In particular, back when we had no inner core. So here, if you can see the inner core radius here, this is just an example thermal evolution, that before you had an inner core, you had no mechanism to generate magnetic field because the conductivity is so high, thermal convection seems impossible. So without an inner core growth, we're kind of screwed. And he dubbed this the new core paradox. The challenge is how to maintain a field there before inner core nucleation. And I should mention, this is still an issue. We're still battling with this, but getting the conductivity down to 80 helps a little bit. Okay, so what about this issue of conductivity? So we just talked about the thermal conductivity. And okay, I've already shown you this now a couple of times. This is the ratio of induction to diffusion. But there's an interesting contradiction in this equation. If you use the Wiedemann-Franz law, as we just mentioned, so I've just rearranged it here. In this equation, you see that as the conductivity goes up, you expect the electrical conductivity goes up. But as the thermal conductivity goes up, you expect the velocity to go down. And that's because you can conduct more heat out. So it doesn't need to convect the heat out. So if your conductivity is high, the velocity is going to go down. So this is the contradiction that, well, what's going on here? U's going down, but sigma is going up. So what is RM doing? And to find that out, we did some math and rewrote the magnetic Reynolds number as a function of just sigma. So I've gotten rid of K using Wiedemann-Franz, and you can see here that sigma appears twice. There's sort of a coefficient in front. Alpha is like 2/5 roughly. So this sort of limit is what I call it in the paper. This conductivity limit is just, you need a metal, you need to have a high conductivity to induce. But this second term here, this has to do with the convective heat flow. And when the conductivity is high, the velocities go down. So you can see it's inversely proportional to sigma here. And this sigma crit limit, I just replaced a bunch of symbols that were up here, this mess. This is just a laundry list of material properties in the mantle and the core. And then if you plot this out, just as a function of electrical conductivity. So obviously Earth has one electrical conductivity, so I put it here. But it's interesting to see these curves have a peak at particular conductivity, which means, and these different colors are just different CMB temperatures. But the fact there's a peak here means that there's sort of an ideal material parameter for inducing the field the best, generating the strongest field. So there is in nature sort of like some preferred conductivity in this regime space I plotted here. And it's interesting to think about as the magnetic Reynolds number gets too high, we think you transition from a dipolar field where the Earth core has a magnetic Reynolds number of about 1,000. But if it gets too high, you can slip into a multipolar type of magnetic field. So these peaks actually could occur at multipolar fields, which don't always extend out to space. And so it might actually be hard to see these in nature unless your dynamo is like really shallow. That's just kind of an aside. Okay. Another way of distilling that conductivity limit is by plotting the electrical conductivity versus the temperature, the CMB temperature. So here is how we think the Earth's electrical conductivity has evolved with temperature over time, just this black curve. And here it is today, of about 4,000 CMB temperature. Now, The conductivity limit I just mentioned is this crisscrossing line. So if you're below this conductivity, you're safely in a thermally convecting region. If you're above it, you can be in a stratified non-convecting dynamo region. And then if you're to the left of this special temperature, then you have inner core growth going on. So this is this core mental boundary temperature at which the inner core nucleates at the center of the planet, which is about 4,100 Kelvin, plus or minus like 400 Kelvin or something. Well, big uncertainties on these numbers. But the game is that you want your dynamo evolution to avoid the no dynamo regime, at least for the Earth, because we know it had a dynamo. And this is sort of our best guess back in 2019 of where this evolution goes. I put it right on this boundary in sort of intentionally, because we think it's sort of marginal for thermal convection today. We don't know the CMB heat flow very well. We don't know the thermal conductivity very well. But then at some point, of course, your core will get so, inner core will get so big, it'll just freeze out. And so this is one limit where the dynamo would die at some point. So once you get all the way over here. And so this is an interesting way of thinking about planetary evolution. So in a later review paper with my colleagues at Carnegie, we put this together for Mars core, given our best guesses back then at what Mars core structure and thermal state looked like. And we would predict that it went through a thermal dynamo phase and then stratified and then is sitting in the no dynamo regime today. Slightly more complicated if you're going to invoke inner core nucleation on Mars. Doug and I have a long paper on this. So go talk to Doug about that and he can answer all your questions. Okay. Venus, this one's unpublished because it's very hand-wavy. But what I've done here is sort of moved these three curves arbitrarily, lowered the core liquidus, increased the mantle viscosity, which pushes this boundary down, and increased the core conductivity, which is a bit unnecessary here. But just to emphasize that Venus could be in this no dynamo regime today and could have passed through a dynamo. We expect it to have passed through a thermal dynamo regime initially. Question is, when did it cross this boundary? And are there surface rocks showing that history? Okay, great. I've gotten a little bit farther than I thought. So I've got a couple more minutes to go through a little bit of this research vignette of what is Earth's inner core age? So what age did it first nucleate at the center of the core? Is there evidence? How would we see that? Because we don't have paleoseismology with that kind of precision, obviously. And what are the potential implications of that age? Okay, so who cares? Well, if we could pin down this TICN, the age of inner core nucleation, it would give us an extremely valuable data point, and that is the temperature at the center of the planet at a time in the past. So we don't have this, right? This is really valuable. Even if it's 4 billion years ago, it's valuable. If it's 500 million years ago, it's valuable because it tells us how the planet has cooled at its deepest in its center, okay? So it's really extraordinary that we can actually get at such a data point. If the inner core turns out to be very old, then it implies most of the geodynamo history has been driven by inner core growth. We don't have to worry too much about the thermal conductivity too much. If it's a young inner core, however, then that implies most of the geodynamo history has been actually thermally driven, which is a little bit more surprising, perhaps. Here's just a smattering of previous predictions of inner core age. And some paleomagnetic data. This is sort of an older one here. Aubert sort of had a huge range in potential inner core ages of like 1 billion to 2 billion. Nimmo's treatise on geophysics has it about 500 million years old, which is the same we got in 2014. So this is kind of a busy plot. I'm going to show this again, though. This is the dipole moment history predicted from a thermal evolution model in the solid black. And then these are paleo intensities binned up in time. Biggin had a Nature paper in 2015 that claimed that this peak here at 1.3 was a signature of inner core nucleation. This has since been shown to be, these data are bad because they've not been demagged to a high enough temperature. And so these are likely overestimates of the actual magnetic field in the rocks. These are all old paleo intensities right here, this kind of strike here. Anyway, so that is sort of where the field was for a while. I already showed you this intensity history, but I just wanted to point out the big inner-core nucleation time was about here, and our sort of simple thermal evolution prediction was about 550 million years ago. So that was the first publication of such a young inner core. And part of the reason why we came to that conclusion was because we knew about this new core paradox that Peter Olson pointed out, that the dynamo could have died, and we wanted to avoid that. And to avoid that, you need a young inner core. You need the core to be cooling quickly, which means that as soon as that inner core nucleates, it's going to grow pretty quick to its current size. Okay. Okay, already shown this. Here's the initial scaling law in blue from our 2014 paper. I don't think this explains the data very well. I mean, certainly I don't think we see this kind of trend here. Maybe a flattening here, that's okay. There's two problems with that. I'm not sure I believe the scaling, these magnetic scaling laws here and these blue lines, but also where's the data? Like we have nothing to compare to. So like, what are we doing here? So that's changed a little bit. I'll come back to that. So what we did in 2016, actually, this is just me, was take these thermal evolution models and stick them into evolving numerical 3D dynamo models. So let's really see what the magnetic field looks like. Okay, this is just a snapshot or an animation of what the models look like. So it's a full 3D spherical shell, a solid inner boundary where the inner core is, insulating outer boundary where the mantle is. So you're just looking at the core fluid here. So modeling the temperature, the fluid velocities, and the magnetic field. And there's a massive caveat you always have to mention when you talk about dynamo models, and that is that we are not in Earth-like physical control parameter space, for the simple reason that the Earth's core is up here at about a Rayleigh number of 10 to the 25, an Ekman number of 10 to the minus 14. These are just extreme numbers, and you would need some massive amount of computers. Chris Davies worked this out a couple of years ago, that you would need 36, use all the computers you can get your hand on at like an Ekman number of 10 to the minus 9, it would take you 35 actual years to get one magnetic diffusion time. So that's a terrible PhD project. That was the point of this paper, right? I think he would already graduate at that point, but okay, this figure is kind of old. This was like my PhD, and now we're pushing, people are like 10 to the minus 8 now. So we're getting there, but we're never gonna get there, is the point. So we have to think about dynamic similarity. Let me go back a slide. That there's similar physical behavior all the way along this projection into the other part of parameter space. This is the idea of dynamic similarity, which fluid dynamicists use all the time, because often you cannot do laboratory experiments of the processes you need to. Okay, so here's the result of this evolving dynamo model. Here's the heat flows over time, and here's my predicted models. There's 25 dynamo models, each at a snapshot of these heat flows. And you're seeing here the dipole moment, the average dipole moment in the center of the circle, and the error bar is its standard deviation. And you can see there's a prediction that the field was relatively weak 2 billion years ago, or it says that I call it a strong multipolar field. And then it transitions to a strong dipolar field about 1.7 billion years ago. And then about 1 billion years ago, it slips down into this very weak non-axial magnetic field. Oh, yeah. And then it recovers. So the inner core nucleation is this little black dot here, and then when it fills the symbol, that's the correct inner core size today. And so it kind of hits this strong dipolar branch and just kind of stays there. Even though the heat flow is still evolving, the buoyancy fluxes are still evolving, but you're on this kind of like stable branch. So it turns out that this picture of sort of these smooth secular cooling lines do not map into magnetic field intensity or morphology space directly. There's more like there are stable branches you get to in these actual dynamo models. And here I'm showing you some snapshots of right before inner core nucleation. You can see all the temperature gradients are near the outer boundary, and that's because it's being driven by cooling from the mantle. And you get this weird 9-dipolar, very weak intensity field. And then when the inner core nucleates, you push all the compositional buoyancy gradients down to the inner boundary, and you produce a weak dipolar field. And then the present day is kind of more distributed, and it's also dipolar. Oh, these are movies that I'm going to skip. It's of the same thing. Okay, so here's comparing the previous plot, but now I'm showing in green my evolving dynamo. And okay, it's interesting, but it's still not convincing to me. But we have some new data now. Oh, well, one prediction was that this weird non-axial magnetic field that I predicted down in here implies that some of the plate reconstructions might be misguided. People see that the magnetic pole seems to be tilting so dramatically that people have interpreted this as plates moving very quickly across the surface of the Earth, so-called paleo-continental reconstructions, paleogeographic reconstructions. And I sort of brought up in this 2016 paper that maybe this is not a tectonic problem, maybe this is a magnetic problem. And there's other snowball events and other interesting things going on during this time. So here's just a laundry list of papers that have pointed out anomalies around 700 to 500 million years ago that I think are all relevant to this intercore nucleation event. And proposed explanations in literature are like extreme true polar wander. That's the whole crust rotating around the mantle itself. Non-axial dipole field, this is the one I prefer, or I've actually shown should be the case. Hyperactive dynamo, okay, if you want to call it that. And if these non-axial dipole field was significant, then the near Proterozoic paleolatitudes are probably not super reliable. I wanted to point out there are snowball events, so around 700, 650. There are events where it looks like maybe the whole planet was covered in ice, but some of these paleolatitudes for these sites, showing these boxes here from this paper, I think could be unreliable if the field is not dipolar at the time, because these paleolatitudes assume you've got an axial dipole field. And if it's not axial dipole, then these paleolatitudes are going to be wrong. So I think we need to keep this in mind when thinking about how global these snowball events potentially were. And here's all the new data that I was alluding to. Okay, so in 2019, they found a very weak field intensity at 530 something. Some more here. This is more like 700. 550, very weak fields. Present day is up here. And then here is a synthesis with a couple new data points. I don't like this curve here. I think this is kind of nonsense, but it is interesting. We're starting to fill in here. And people think this red square here, this one, may be at the first signature of the recovery of the field after the intercore nucleated. So it's sort of, the magnetic field was coming close to death, and then the intercore sort of saved it, if you want to think of it in a very overly simplified way. Okay, and I'm not going to talk about that, and I'm going to skip to the ending, so we have some time for questions. So my conclusions are pretty broad, but that if you're going to take one thing away, it's that planetary dynamos are ubiquitous, and they're really cool and useful for probing what's going on in the interior of these planets. And Earth's own magnetic history is ripe with lots of interesting stories that we're still unraveling. And people are now starting to write papers, not me, that the Cambrian explosion was actually triggered by the intercore nucleation. So I'll leave it at that, and you can look those up on your own, and I'll take questions. Thanks.
All right, thanks, Peter. Let's start with a couple of questions from students, if we can. Got any student questions? Yeah, Emma.
Great talk. Thank you. It's very interesting. Lots of patterns to see, I guess. Oh, sorry. I guess, so you have this sort of instability in the dipole moment right before your proposed nucleation.
Yeah.
Could you, I guess you said, oh, that could be like an oversimplification of things, but could you look at like patterns of instability in other planets and say anything about its like either transition to another regime or its its evolution of cooling?
Yeah, like if the moon went through a similar phase, and was generating solidifying basalts on the surface during that magnetic field phase, which was not a given, then the moon would have a similar record, and that would be awesome. But I think we'd need to go get some really careful measurements, a lot of them, because you don't know, you're trying to get the right age. You're trying to get rocks that have been well preserved. So the paleomagnetism is hard. You know, I kind of skipped over all of that because it's not what I do. That's a hard game. Not a lot of people in that field, unfortunately. It's kind of like, was like the birth of plate tectonics came out of paleomagnetism in a lot of ways. And it's kind of slowed down a lot. But hopefully there's a resurrection here with the renewed interest in the lunar field and the lunar history, and possibly other planets too. Well, why not? Yeah.
I guess the reason why I was asking this is, and I know you were talking about rocky worlds, but in the very beginning you showed Uranus and Neptune had a very non-dipole dynamo. So I guess, what do you think about? Are they unstable or?
Yeah, that's a great question. I probably, my default guess would be they're in the kind of multipolar instability regime, which you can get pretty easily in numerical models by just increasing the fluid velocity, decreasing the scale of the flow in the magnetic field. You tend to get these multipolar fields. But whether they're in that state sort of quasi-permanently, or it was going through a transition when Voyager flew by, I don't know. Like, we don't know. Maybe Krista has lots of papers on this, so you can ask her for more. But yeah, good questions.
Clearly someone else. Okay, if there's no more student questions, we'll go in the back. There's Sean and Thorsten had his hand up too.
Yeah, just curious about whether there would be a prediction from core melt to boundary temperatures and boundary flux that mantle plumes would have some correlation to this, core creation event, this inner core creation event that would then allow a predictable thing that we could look for.
Yeah, I did take a brief look at the LIP databases, the large igneous province databases, to see if there was an obvious spike. I didn't see one. Yes, there are lips around the time you would expect a plume of heat associated with inner core growth to make it to the surface, but there are lips in time before and after that. So it's not a very strong signal, but potentially, most of the work the inner core is doing is driving compositional convection. So it's really going to change the magnetic field in that way. In terms of the heat pulse you get from it, it's very limited because it's just latent heat, really, which is like a 1/10 of the heat budget, and even less of the mantle. It's like maybe 5% of the mantle heat budget. So it's marginal, I think. It's a good question, though.
It would be mainly controlled by the change of the internal heating of the mantle over time, in terms of the balance of plumes to slabs, right? And so there isn't much of a trend there, and you would have to see it on top of that sort of long-term secular decrease of the internal heating. But my question is, if you could comment a little bit on this debated issue of maintaining atmospheres with a field or without, and just sort of what your thoughts are on how much we understand that and how relevant the field is for the atmosphere?
Yeah, that's a hard one because we only have a couple planets with atmospheres and magnetic fields. Actually, one. And obviously Venus has a massive atmosphere, no magnetic field. So there's no simple correlation here. My best guess is it's really protecting the hydrogen. Because the magnetopause is way up there. It's like 9 Earth radii. And the only stuff up there is hydrogen, mostly. And it's hydrogen that Venus has lost. You look at the deuterium ratio. So back in 2013, we have a model of atmospheric escape that shows you can get Venus's atmospheric evolution with a magnetic field that died and so forth. So the whole show the whole story in 2013. That escape model has not picked up any traction because there's really no data. Like until we have some planets with some magnetic fields and some atmospheres to kind of back it out, like no one's really going to believe you, right? So I think we're kind of stuck at the moment. Maybe exoplanets will help, maybe, but it's tricky. Yeah. It's also not my field, I should say. Like atmospheric space physics is a whole nother type of MHD, right? And so maybe people working on that have more ideas. So
Let's take one more. Yeah, I think she had her hand up. Oh, sorry. Maybe two more. Greg, if she's questions quick.
Okay, I have great talk, Peter. I have okay, 3 questions. I'm trying to fold in one question. So first of all, I'm looking at that figure, and now I think I figured it out. Is that sort of like in the center, which looks like an eye, is actually the growing inner core boundary?
exactly. You're just looking in through the circle there.
Awesome. Cool. The that was my first question. My second question is more technical. Like in your 2 billion year, like the Earth's magnetic field evolution history, when you have like the inner core growing, that kind of scenario, do you use different heat mechanism? So for example, when you have no inner core versus a growing inner core, do you use like a mixed bottom heating versus internal heating to represent different heating mechanism?
Yeah, so it's, some of that information is in this plot here. So the black is the total buoyancy
Mm-hmm.
flux or power, if you want to call it. The blue curve is just the thermal one. The red is the compositional one. And then I have a sink of compositional so that I don't build up light elements in the core. But the total is the black one. So you can see, yes, and the buoyancy location does change. Like the thermal cooling is occurring here at the top. The compositional buoyancy is occurring here at the bottom.
Mm-hmm.
Yes.
I guess that lines up with like the bottom heating mechanism would act to stabilize the field. So maybe that's one part of the reason you have a like stable dipolar field that's non-reversing. Okay, cool. My last question is whether you have like what's your opinions on how we can get a better understanding of Mars magnetic history? Because right now we only have this crustal and a sample of different meteorites and all that.
Yeah, well, there's the easy answer, which is like send more, get more data, send more probes, blah, blah, blah. So we should definitely do that. The harder answer is what can we do? I think I do have a desire to look at, you know, to play a game like this, like I did for Earth with the other planets. It's harder because this thermal evolution is much less constrained for the other planets. For the Earth, I have some constraints on that. The other planets, I really don't. That said, we can still play this game and see if we have any interesting magnetic field evolution that could somehow look like the strange crustal fields that are there. It's not going to be simple. You have to think about how that works, but yeah, that's kind of all we can do though. Like, you know, like, and the more constraints we can get on Mars evolution, the better. So heat flow would be great. That didn't really work out. An inner core measurement would be great because then we'd get some constraint on the temperature of the core and the composition and so forth. So really need more constraints, but there's still more we can do, I think, in that space. Okay, thank you.
Let's give Greg the last question. And while the mic's getting on its way over there, I'll just point out that the students are going to take Peter to lunch in a minute. Travis right there in the middle is going to be coordinating that. So any students who want to join for lunch, what are you meeting in the lobby at like 15 minutes? Okay. Greg.
Great talk. I'm very interested to speak with you later in the day. But my main question is, if we look at Uranus and Venus, they both have interesting orbital and rotational parameters. And an idea is how that happened was by giant impacts. So I'm curious how Earth, or not just Earth's, but just the bombardment history in the early solar system and even through 3.5 billion years could have influenced some magnetic fields.
Great question. I have a paper on this and I'm working on this problem now. From the perspective of giant impacts, what they do, how they heat the core. What do they do to the core? What do they do to the core thermal state versus planets that don't suffer sort of core merging giant impacts? And what we found in the first paper was that you tend to heat up the top of the core, not the whole core. Like the impact heating does not, most of the impact heating is at the top of the mantle and sort of decays away as you get deeper into the planet. That's just the impact shock heating. But the actual merging of like the impactor's core, like Thea's core, is thought to have merged with Earth's core, and it gets massively shock heated. And so Thea's core would create this big thermal blanket on the top of Earth's core that would suppress dynamo action and convection and dynamo action. And from what we get from the models, it looks like for the Earth, it would delay. You have to get that heat out in order to turn the magnetic field on again, or for the first time. So it looks like you would have a delay of about 300 million years, 200 million years between the last giant impact and dynamo onset, thermal dynamo onset. That's a very rough number, but we are thinking along those lines of like, what are the initial conditions and to what extent do they depend on impacts? Yeah, that's a great question.
Thank you.
All right, if you have more questions for Peter, we're going to go to ABW later, so join us for that. And let's thank Peter one more time.